Rohini College of Engineering and Technology from Department of Civil Engineering. So this is our final year civil engineering subject. So final year civil engineering subject is C8703 Structural Design and Drawing. So I am Michael Theodore, Assistant Professor. So today we will say of the topic is design a steel roof truss. So unit 4 industrial structures. So design of steel roof truss. So design a steel roof truss to suit the following data. So span of the truss is equal to 12 meter. Then type of truss is equal to pan type. Then roof cover is equal to galvanized corrugated sheet. Then material is equal to rolled steel angles. So spacing of roof truss is equal to 5 meter. Then wind pressure is equal to 1 kilonewton per meter square. So draw the elevation of the roof truss and details of the joints. So solution step number 1, dimensions of the truss. So central rise is equal to span by 4. So we know the span length is the 12 meter. So 12 by 4 is equal to 3 meter. So purlins are provided at the intervals of 1.863 meter on the principal rafter. So see the diagram. So mark all the values. Then span is the 12 meter. So split into 4 divided by 2. So 12 divided by 3 is equal to 4 meter. So split the angle. This is a pan type okay. So our inclined angle is the 1.863 meter. The next. So step number 5, design of purlin. So step number 5, design of purlin. For continuous purlin, the maximum factored bending moment and shear force are computed as follow. So M is equal to WL square by 10. We know the bending moment formula. So 1.5 into 1.5 is the factored load and W is the 1.3 and 5 is the length of the cell. So M is equal to 4.89 kilonewton meter. So V is equal to shear force. So 1.5 into load W is equal to 1.305 into 5 divided by 2 the 4.9 kilonewton. So adopt ISA 100 into 7 into 8 mm having section properties given below. So Zx is equal to 4.38 into 10 power 4 mm cube. So D is equal to 100 mm, then B is equal to 75 mm, and T is equal to 8 mm. Then it will be class from IS 800 2007, class number 3.7. So check for the section. The classification done by computed the ratios. So we know that some of the ratios are in our code book. So B by TF is equal to B. We know that B value is 75 and T value is 8. So B by T is equal to 75 divided by 8 is equal to 9.37 is less than greater than the 9.37 is less than 9.4. So hence the section is considered as the plastic section. So check for shear capacity. So AV is equal to B into T. So B is the 100 and T is the 8. So 800 mm square. So class number 8.4.1 AV FYW divided by root 3 into gamma M0. So we know all the values. Just apply the values in that formula. So you got the answers. So 105 is greater than the 4.9 kilonewton. So hence safe. The shear capacity of the section is very large. So the shear capacity of the section is very large compared to the applied shear force. So the section is already hence safe. So next the check for the moment capacity. So we know the formula MD is equal to beta B Z into Fy divided by gamma M0. So in this formula is in our code book IS 800 2007. So beta B is 1 into Z is equal to 4.38 into 10 power 4. So Fy is equal to 250. So divided by 1.1 is equal to MD is equal to 9.95 kilonewton. So is greater than 4.89 kilonewton meter. So hence safe. So step number 7, load on truss. So dead load. So sloping length of the rafter is equal to root of 5 square plus 2.5 square. So it's equal to 5.59 meter. So spacing of this truss is 5 meters and to some distance. Then weight of the GC sheet is as per planned half truss means the full length is the 5 into 5 is equal to 0.18, then 4.5 kilonewton. So weight of purlin is equal to for 4 numbers at 0.1. So 4 into 0.1 into 5 is equal to 2 kilonewton. So self weight of roof truss is equal to span by 300 plus 0.05. So you got the answer is 0.083 kilonewton per meter square. Then total load of the half truss is equal to, add the total load is equal to 4.5 plus 2 plus 2.0575 is equal to 8.57 kilonewton. So dead load on intermediate panel point is equal to 8.57 divided by 3 is equal to 2.85. Because of this intermediate panel, so divided by 3. So sometimes the end panel, so divided by 2. So next on the dead load on end panel, so 2.85 divided by 2 is equal to 1.425 kilonewton. Then live load is equal to, so live loads on half on truss, so 0.52 into 5 into 5 is equal to 13 kilonewton. So wind loads is based on this. So maximum wind load perpendicular to the sloping surface. So wind load on intermediate panel is as well as same as the intermediate means divided by 3 and end panel is divided by 2. So step number 8, design of truss members. So member A, B, B, C and C, D. So maximum service load compressive force is equal to 36.17. Then factor load, it is simple, multiplied by the constant factor load is a 1.5. So 1.5 into 36.17 is equal to 54.25 kilonewton. So as well as same as the maximum service load tensile force. So the tensile force is 22.95. So multiplied by the factor load 1.5. So length is equal to 1.863 meter. So effective length KL is equal to 1.8304 meter. So try two angles ISA 50 into 50 into 6 mm. So placed back to back. So area is equal to 1136 mm square. So minimum radius of gyration or minimum is equal to 15.1 mm. Then slenderness ratio is equal to KL by R minimum. So this formula is on code book, page number 20. So stress reduction factor for A corresponding to the slenderness ratio. So Fo is equal to 250 Newton per mm square. Then design compressive strength and design compressive force is to be computed by the, so compressive strength means FCD. So FCD is computed by the some formulas. So and design compressive force is the given by, so design compressive strength is given by PD is equal to A into FCD. So we know that area 1136 and FCD is the previously we find out 112. So it's equal to 127 kilonewton is greater than 54. So hence safe. So remember DE is the same as the maximum load tension, then factor load tension, then again normal load it multiplied by the factor load, then maximum service load compression we know again multiplied by the factored compression load. Then the effective length is equal to 3 meter. So we'll try a single angle ISA 50 into 50 into 5 connected by 6 mm gusset with a junction with a bolt of 16 mm at 50 mm. So gross area is equal to 479 mm square. Then aluminum is equal to 15.2 mm. So provide using 16 mm dia bolts. So we can use the strength and govern by the rupture of critical sections. So we know the formulas. So in the formulas in our code book, just to copy from that. So you know all the values, just apply the values here, you got the answers. So TDN is equal to 0.9 into 160 into 410 divided by 1.25. So our TDN answer is 83.02 kilonewton. Then strength governed by the yielding of stress cross section. So TDG. So this from also from our code book. So AG is the area of cross section. So Fy is the given in our question. So gamma M0 is taken from our code book, page number 30. So strength governed by the block shear. Block shear means AVG, ATG and ATN values are found out. So the block shear is the smaller of the values of TBN and TB2 is the computed the equation below. So this formula is in our code book. So AVG is a 500 and TB1 is equal to 99.92 kilonewton. So TDB is equal to, apply all the values, you got a 109.22. So hence TDB is equal to 109.12 kilonewton. So under the three values computed, so the decision shear strength is take the least value for this section. So because of 108 is there, 83 point is there, then 109 is there. Take the least value is the TDN means 83.02 is the least value. So it will be greater than 19.24 kilonewton. So hence safe. So remember CB and EB. So compressive strength, then tensile force is the compressive force is 6.95. Then again multiplied by the factor load. So you will give the 10.42 and tensile force is 6.38 and again multiplied by the factor load the 9.57 kilonewton. So effective length KL is equal to 0.7 into 1.6 meters equal to 1.12 meter. So use minimum size angle ISA 50 into 50 into 5 mm. So the areas or minimum radius of garrisons, all the values are taken from our code book. So the stress reduction factors corresponding FO is equal to 250 Newton per mm square, and design compressive strength is, we know the already that formula. So step by step we can use that same formula, so you can easily understood that. Then FCD is equal to all the values are, if you know that, you're gonna apply and you got the answer. So FCD is equal to 78 Newton per mm square, and design compressive force is given by PD is equal to A into FCD. So 37.36 is greater than 10.42, so hence safe. So member EA and EF, so maximum service load tension in is equal to 32.21, so multiplied by the factor load means into 1.5. So again also maximum service load compression load also do that same procedure, so it's 18.84, so multiplied by the 1.5 is equal to 28.26. so length of the member is equal to 3.33. then again you find out the effective length so design strength due to yielding of cross section. So TDJ is equal to AGFY by gamma M0. We know that simple formula. So AG value is a known value, then FY is a known value, then gamma M0 is a known value. So TDJ is equal to 258 kilonewton. Then design strength governed by tearing at net section. So TDN is equal to normal formula, assuming a single line of 16 mm bolt of two numbers and spacing 50 mm apart. So TDN is equal to 75.5 kilonewton. It is greater than 48.31 kilonewton. So hence the section is safe. So hence the angle section designed for the truss can be safely resist the factored loads. Thank you.